Here's the free response from the Chapter 10 assessment on solids and liquids. There are two different versions to some of the parts of this first question. In both, you were given two giant organic carbon structures and asked to list all types of intermolecular forces the compounds have in common. So they always have London forces, where the electrons might be moving in a way that does not evenly distribute them throughout the molecule. They're also both polar molecules, and we've got these polar regions of carbon and oxygen. Like there's a polar area, here's some polar areas. So they could both have the dipole forces. Here's some polar groups. Carbon and oxygen is polar. That oxygen will pull the electrons because of its high electronegativity. This area is going to be a little polar. The nitrogen has a higher electronegativity than carbon. So they can both have dipole forces in between the molecules, but they don't both have the chance of hydrogen bonding. In order to have hydrogen bonding between the molecules, you've got to have really polar groups. That would mean hydrogen directly bonded to an FON. The first compound has that option. In compound X on the left, we've got OH groups that are really polar. In compound W on the right-hand side, we've got that nitrogen-hydrogen group that's really, really polar, but not in compound Y. So just London and dipole forces. On the left-hand side, it says compound X has a higher boiling point than compound Y. Cool. The student claims that the difference is because compound X exhibits hydrogen bonding and Y does not. Do you agree or disagree with the claim? So sometimes I think we have to read this one carefully. We're going to say, yes, we agree with the claim. That's what they wanted us to describe. Not that we're agreeing or disagreeing that X has a higher boiling point. Like they're telling me that. They're telling me that X has a higher boiling point. We had to agree or disagree with the student's claim. Is that higher boiling point due to hydrogen bonding? Yes. That polar OH group is going to cause stronger intermolecular forces. So yes, compound X would have a higher boiling point. On the right-hand side, again, they're telling me compound W has a greater boiling point than compound Y. So I'm not going to dispute that. I'm not saying that I agree or disagree. They're telling me that W has a greater boiling point than Y. This time the student claims that the difference is because compound W will have greater dispersion forces. And then we're going to disagree with the claim. That's what they wanted me to answer. Like, do you agree or disagree with the claim? Well, the reason why W's got a higher boiling point or stronger intermolecular forces is due to hydrogen bonding. I've got those insanely polar groups where the nitrogen is bonded to hydrogen. That's why the boiling point is higher. In both compounds X and W, it's because of the hydrogen bonding. It's because of the stronger intermolecular forces. In part C, we were to draw a water molecule in proper orientation to show hydrogen bonding with this methanol molecule. And you could have done this either way. Number one, we want to show that the water molecule is most attracted to that OH group. That's the region that's the most polar. The electronegativity of carbon and hydrogen is, it's a little different. I think carbon's electronegativity value is 2.5 and hydrogen is about a 2.1. So yeah, carbon might pull a little bit on the electrons, but it's way more polar on the OH end. So that's where the water molecules will show their strongest attraction. That's where I'm going to show a hydrogen bonding in between molecules that both have these really, really polar groups. So the hydrogen will be partial positive, the oxygen are partial negative. You could either show the water molecule being attracted to the hydrogen dangling off the end, or you could show that the water molecule would be attracted to the oxygen on the end of the methanol molecule. We just have to make sure that we show them in proper orientation. Partial positives attracted to partial negatives. But either would have been acceptable. Part D was the part that was missed the most. And I think it's just a reading issue. The vapor pressure of liquid methanol is about 92 torr at 20 degrees Celsius. The vapor pressure of liquid benzene is less at the same temperature. Which compound will have stronger intermolecular forces? Explain in terms of the types and strengths of intermolecular forces between both molecules. Okay, so my first thought, if I weren't given any data, I would assume that the methanol's got stronger intermolecular forces. There's an OH group on the end. But I have to look at the data that I'm given. The vapor pressure of methanol is actually higher than the benzene. And a higher vapor pressure means lower intermolecular forces, weaker intermolecular forces. It means that those methanol molecules are more likely to evaporate, go off into the gas phase, bounce around, and create pressure. So now I have to come up with an explanation on why a polar molecule like methanol, which should have hydrogen bonds, is actually going to have weaker intermolecular forces than that benzene. And if I look at the structure, like the benzene was non-polar. I think they gave you the structure in the test. It kind of looks like this. You've got carbons in a little ring, and they alternate, single bond, double bond, all the way around the ring. And so then you just have a hydrogen dangling off each carbon to give the octet. It's totally non-polar. Like every carbon has the exact same kind of bonds. It's going to be one of those resonance structures where the double bonds kind of flip-flop or rotate around the ring. Totally non-polar, very balanced. But yet with a lower vapor pressure, it must mean that the particles are more attracted to each other. Their intermolecular forces are stronger. And we had one of these as an example. The explanation is electron count, polarizability. There are times when you could have a molecule that has stronger London forces than the hydrogen bonds of another molecule. And it must be that there's significantly more electrons in that benzene molecule, so it's more polarizable, and those temporary charges could be stronger than compared to the charges on that OH group. Greater polarizability. There's just more electrons in that C6H6 molecule. Again, I wouldn't be able to answer this question without that data. Without the data, I would have assumed that it was the methanol, which I think was the most common wrong answer, where people talked about hydrogen bonds. But oh wait, I had to look at those vapor pressures. It's not what I expect. Part E. You had two options, but they're both good to look at, and there's two ways that you could have solved these. I've got the heat of vaporization of benzene or methanol, and we want to know how many grams of liquid benzene or methanol can be vaporized with the addition of 50 kilojoules of energy. So you could set this up a couple ways. The definition of heat of vaporization is that it's the amount of heat needed to vaporize 1 mole, kilojoules per mole. Well, then all I have to do is multiply by the moles that I do have to figure out how much energy is needed to vaporize my sample. In this case, I was given the 50 kilojoules of energy. That's the amount of energy I have. And I want to know, like, how many moles can I vaporize? If I know moles, then I can just turn moles into grams. So you could set it up like in red, where you've got the delta H, that's the 50 kilojoules. I'm going to solve for moles, and I know the heat of vaporization. And in both of these, it kind of makes sense. Like, I've got 50 kilojoules of heat available. It takes about 31 to 35 kilojoules to vaporize the benzene or the methanol. So yeah, I should be able to vaporize like a little more than 1 mole of each. And then I can turn that into grams. Or in green, you could set this up like little ratios. The heat of vaporization is the amount of energy needed to vaporize 1 mole. If I have 50 kilojoules, how many moles could I vaporize? Same calculation, just maybe a little different setup. Once you've got moles, then I can change that to grams by using the molar mass of benzene or methanol. And the last one, number 2. I've got 2 non-polar molecules. CH4 is a gas at room temperature, whereas the carbon tetrachloride is a liquid at room temperature. Explain this observation in reference to the types of intermolecular forces in both substances. Well, again, they're both non-polar, so they're both just going to have weak London dispersion forces. But because the carbon tetrachloride is a liquid, the attraction must be a little stronger. The London forces are stronger. Well, again, it's that polarizability. There's more total electrons in the carbon tetrachloride. So with more electrons, there's just a greater chance that they're not evenly distributed in the electron cloud. Greater polarizability results then in like a greater chance of getting partial charges. And then in part B, I've got some carbon tetrachloride liquid placed in a previously evacuated container, which just means empty container, at 30 degrees Celsius, where some evaporates. In the box below, draw a particle diagram to show the species in the container after some of the liquid has evaporated. The phases of the species should be indicated by the spacing and distribution of the particles in the diagram. All you had to do was draw that same carbon tetrachloride molecule, but show them in the gas phase. So instead of them being kind of close to each other in the liquid phase, just show them spread out, maybe like occupying the entire container. But I do not need to break them down. Evaporation is a physical change, so it's the exact same carbon tetrachloride molecule. It's just that they're in the gas phase. They're more spread apart, maybe a little higher energy.